Welcome to this lesson on sampling distributions for sample proportions. This is a foundational topic in AP Statistics that bridges the gap between descriptive statistics and inference. Our learning objectives are 1. Calculate the mean and standard deviation of a sampling distribution. 2. Verify the conditions for normality. And 3. Interpret these values in context. By the end of this video, you will be able to determine the center, spread, and shape of a distribution of sample proportions and justify whether a normal approximation is appropriate. Let's start by defining our terms. In statistics, we often want to know a population proportion, which we call P. However, we usually only have access to a sample proportion, which we call P hat. If we took many samples of the same size and calculated P hat for each one, those values would form what we call a sampling distribution. Think of P hat as a random variable that changes from sample to sample. Today, we're going to learn exactly how that variable behaves. Every sampling distribution has a center and a spread. When we talk about the sampling distribution of a sample proportion, we have specific formulas for the mean and standard deviation. Our objective is to calculate the mean and standard deviation of a sampling distribution for a sample proportion. First, let's look at the mean. The mean of the sampling distribution of P hat, denoted as mu sub P hat, is simply equal to the population proportion P. This means that P hat is an unbiased estimator of P. On average, our sample proportions will hit the true population proportion right on the mark. Next, we have the standard deviation, denoted as sigma sub P hat. This measures how much we expect the sample proportion to vary from sample to sample. The formula is sigma sub P hat equals the square root of P times 1 minus P, all divided by N. Here, P is the population proportion and N is the sample size. Notice that the sample size N is in the denominator. This is a crucial observation. As our sample size increases, the standard deviation decreases. In other words, larger samples give us more precise estimates of the population proportion because there is less sampling variability. Take a moment to think about that. Why would a sample of 1,000 people be more consistent than a sample of 10? It's because the larger group is more likely to mirror the true diversity of the population. Before we can use these formulas or assume a normal shape, we must check 3 critical conditions. These ensure our model is a reliable representation of reality. Our goal is to justify why these conditions are appropriate for the sampling distribution. The first is the randomization condition. We need to ensure that our sample is representative of the population. Without randomness, our results could be biased and the math we're about to do wouldn't apply. The second is the 10% condition. This is specifically for when we sample without replacement from a finite population. Mathematically, we need the individual observations to be independent. If we take too large a chunk of a population, the probability of picking a certain type of individual changes as we remove people. Keeping our sample under 10% of the total population allows us to treat the observations as virtually independent. Finally, we have the large counts condition, which determines the shape of our distribution. We need to expect at least 10 successes and at least 10 failures in our sample. If this condition is met, the sampling distribution of P hat will be approximately normal. If these are satisfied, we can use the normal model to calculate probabilities. These conditions ensure our statistical inference is valid. Let's put all of this into practice with a concrete example. Suppose it is known that 70% of students at a very large university prefer digital textbooks over physical ones. We take a random sample of 100 students. First, we must check our conditions to see if we can model this distribution. 1. Random. It is stated as a random sample. 2. The 10% condition. 100 is likely less than 10% of all students at a very large university. 3. Large counts. N times P equals 100 times 0.70, which is 70. N times 1 minus P equals 100 times 0.30, which is 30. Since both 70 and 30 are greater than or equal to 10, the large counts condition is met. This tells us the sampling distribution of P hat is approximately normal. Now, let's calculate the mean and standard deviation. The mean is 0.70. This means that if we took many samples of 100 students, the average of all those sample proportions would be 0.70. The standard deviation is the square root of 0.70 times 0.30 divided by 100. This simplifies to the square root of 0.21 divided by 100, which is the square root of 0.0021. The standard deviation is approximately 0.0458. In context, this means that in a typical sample of 100 students, the sample proportion of students who prefer digital textbooks will vary from the true population proportion by about 4.58%. Understanding this variability is the key to making predictions about a whole population based on just one sample. To wrap up, let's review the core concepts we've covered today. You are now equipped to describe the sampling distribution of a sample proportion using three key characteristics: center, spread, and shape. First, we have the mean, mu sub p hat equals p. Next is the standard deviation, sigma sub p hat equals the square root of p times 1 minus p over n. And finally, the conditions: random, 10%, and large counts. We learned that the mean of the sampling distribution is always equal to the population proportion, making it an unbiased estimator. We saw that the standard deviation depends on both the proportion and the sample size. Remember the inverse relationship. As your sample size goes up, your standard deviation goes down, leading to more precise estimates. Finally, we discussed how to justify using a normal model. By checking the randomization, 10%, and large counts conditions, you ensure that your statistical calculations are valid and that the distribution is approximately normal. You can now calculate, justify, and interpret these distributions. When you are solving problems, always remember to interpret your results in the context of the specific population you are studying. This turns a simple calculation into a meaningful statistical conclusion. Great job today! You've successfully navigated the logic behind sampling distributions for proportions.